All right, so really briefly reintroducing Ben. Ben Koschnick is an aerospace student at UNSW, completing his final year. Thanks, Ben.
Okay, so let's try this again. My name is Ben. We are Spectral Aerospace. Our mission is to change the way we see our world. We're a Canadian-Australian partnership developing hyperspectral satellite remote sensing solutions. And there's a few reasons we're doing this. So pipeline monitoring is currently done with aerial hyperspectral photography. This costs the industry billions of dollars in maintenance, fuel, labor, etc. And this can either be done by detecting the hydrocarbons directly at the wavelengths you see there, or we can detect the vegetation next to it, and basically we detect the poisoning of the vegetation as the stuff leaks out. Now, agriculture can also benefit from this kind of satellite imaging. As a single satellite, we move into large patches of agriculture, and while it might not necessarily replace ground monitoring, it does allow for a much cheaper alternative when you're dealing with large amounts of land. It can also be used as a cheaper alternative, it can also be used by third parties to understand market supply and demand in situations like the government trying to avoid like shortages and that sort of stuff. So aquatic river systems are particularly interesting actually, because in a recent study by the CSIRO and the Committee on Earth Observing Satellites, they found 26 bands of interest ranging most of the visual range. They didn't even check the near-infrared for what I can tell, which means that there's a lot of potential there for various things that we can monitor from space. The only problem with this is that there are no dedicated multispectral satellites, and we need a very small ground space distance to monitor small rivers, obviously. Okay. That's only scratching the surface, really. We've come across some pretty out there applications for this kind of technology. We find one every 2 weeks, honestly. With hyperspectral remote sensing satellites, there's really not any limits, and that's the benefit of hyperspectral imaging. Whereas multispectral imaging has 4 to 10 bands that you have to select to complete the jobs that you have when you launch. A hyperspectral imaging satellite solution is flexible. Once you launch it, you've got hundreds of bands there. You can change and you can pivot what your job is, what your application is, and service multiple markets at the same time with one satellite. So we want to build a hyperspectral satellite. What is that going to look like? Well, most of these studies have been done on aerial photography, which is both a pro and a con. Pro in that a lot of the requirements aren't actually as harsh as they need to be, because they don't worry about ground space distance. They can achieve these ground space distances really easy because they're a little closer. The con being is that we need to go out there and do this research and find out what these parameters actually are. Now, while initially this sort of stuff might be more expensive, it is cheaper in the long run, because you're not constantly paying for fuel, you're not constantly maintaining this, you're not paying for any sort of wages for pilots and stuff. Con. By the Rayleigh's criteria, if we want to do pipeline monitoring, which is our big ticket item, we need to launch a satellite with an aperture size of at least 327 millimeters. This means that our final solution is not a Cubesat. So we're aiming for something larger down the road. So with all this in mind, can we produce a satellite that can handle all of these requirements and leave enough flexibility to enable for a wide variety of these niche markets that we can capture? Well, yes. To do this, we need a ground space distance of 5 meters. That's for the pipeline monitoring. And a spectral resolution of 5 nanometers allows for all that river ecosystem management. Agriculture is somewhere in between the two of those. This straddles the visual and near-infrared ranges. The aperture itself would be as large as we can get it. We're aiming for 600 millimeters because that's what a satellite this size usually has. Larger aperture just means a stronger signal, therefore a better signal-to-noise ratio. If we want to achieve a continuous global mapping in the future, we need a 63-kilometer swath. However, this isn't really a requirement, it's just something that we're trying to achieve. It's a goal. Once again, the big market here is the pipeline monitoring. So we're going for that with our return time. They want us to achieve 7-day return times. That's what they do with aerial photography at the moment. So what we're going to do is sit on the 6 a.m., 6 p.m. line. So the parameters you see there in what would basically be a sun-synchronous orbit, except we pass over the same point 21 days, so we're a little bit out of phase. Now, if we pivot a little bit from side to side with about 6.3 degrees, we can achieve that 7-day return time. And then in the future, if we keep adding more satellites to that network, we can get that 7-day return time for the entire planet. So I know someone in the audience is waiting to get me with this one because yes, hyperspectral imaging generates a lot of data. And we're just going to go with the parameters we had before. We're producing 8.42 gigabytes of data every single second. We can't get that to the ground. There's been some really good technologies here today. I don't think anyone can honestly say they can get that continuously 24 hours a day. But the good news is we're not being paid for all that. So we need to be smarter, we need to be more strategic about it. Straight off the bat, what we can do is we can throw out a lot of that data because we're only being paid to image areas around those assets. So that would be the first thing we do. The second little trick we found was that if we take adjacent pixels, we can add them together to basically replicate a situation where we had less resolution, but in that way we produce less data, and as a byproduct, create a higher signal-to-noise ratio. So that can be really helpful as well. We could do all of this on board the satellite, and that helps our data downlink and allows us to do this sort of stuff continuously. We're also trying to keep on top of emerging technologies because if we can get more data, we have more productivity, we have higher productivity on our satellite. So we're working on that. Now, this is the big item for today because we keep hearing about groups that are building new satellites and all that sort of stuff. We're a remote sensing satellite company. We want to build instruments, we want to focus on our data, and we want to operate our satellites. We don't actually necessarily have to build a SmallSat. So, considering that we're in a size range that is kind of coming back into fashion a little bit, depending on which field you're in, especially in remote sensing, where you need very nice ground space resolution. So what we decided to do was that we partnered with Spiral Globe, who you just heard from, and we're trying to create this new separate venture to handle the engineering aspect of this. To do this, we want to make full use of the industry in this room. We're looking for partners, we're looking for suppliers, we're looking for customers. Basically, we want to take as much as we can from the industry as it is, put together the satellites, and sell to the providers. So, if anybody is interested in this at all, come to me afterwards or just contact me online. Basically, this is just us putting it out there to see who's interested in this sort of category of satellite. So, Spectral Aerospace's mission is to change the way we see our world. To spearhead a transition into hyperspectral imaging to allow for a smarter and more aware world. Thank you for your time today. Details online, I'll just ask some questions.
Great job rushing through there, Ben. Are there any questions for Ben?
This is spectral analysis Fourier based, or are you considering other basis functions for sharp feature analysis like wave?
So we're working with, like I said, we're a Canadian-Australian partnership. So my co-founder's in Calgary. He's working with a group of people over there who are trying to put together AI solutions for this sort of stuff. So that would be machine learning, algorithms, and that kind of thing. If you want more details, you can contact me and I can pass you on, but I wouldn't be able to say for certain because that's sort of still working on that.
When would you aim to put the satellite into orbit?
Well, they're doing the aim to do it and when we'll be allowed to do it because of finances and stuff. We would like to have our first satellite up within 5 years. We're aiming for 3, but within 5 years is the goal we're trying to go for. Obviously, that depends on how much funding we get, depends on what sort of technological challenges we come across. So we're still very early stage, so that timeline is rather flexible.
Are you going to build the satellite yourself, or some other company will do this for you?
We're hoping that with the Magpie collaboration, we can get the satellite built in a separate factory so that development costs are shared between companies like us who need these sort of buses. And basically that would be out of their hands. That's not us. focusing on our business model, which is the instrumentation, the data analytics, and the operation of the satellite itself.
All right, thanks, Ben. So, Paris, are you